بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. طلاب المرحلة الأولى Linear Algebra 2 First Level Lecture 12. We complete linear transformation with similar matrices. We have this proposition. Let V1, V2, V3 be vector spaces and phi find from V1 into V2 and psi find from V2 into V3 are isomorphism. Number 1. Phi inverse find from V2 into V1 is an isomorphism. Number 2. Psi circle phi find from V1 into V3 is an isomorphism. This is a proposition. We will prove this proposition. Prove the inverse of a bijection is a bijection. What mean of bijection? Bijection that in the function is 1-to-1 and on to. If function 1-to-1 and onto, we call it bijection. We need only prove the linearity, because this is true for 1. We know phi is isomorphism from V1. That means phi is 1-to-1 and onto and linear. And if phi inverse from V2 into V1, if phi 1-to-1 and onto, then phi inverse also 1-to-1 and onto. So now just we need to prove the linearity. let xy belongs to v2 and c belongs to real number r. Note by surjectivity of a psi there exists AB belongs to V1 such that a psi of A equal to X and a psi of B equal to Y, which means a psi inverse of X is equal to A. If we take inverse for this equation, a psi inverse of X, or this a psi will be identity A will be A, so a psi inverse equal to of X equal to A. This is the same a psi inverse of Y is equal to B. Then phi inverse of X plus Cy, this is two condition, prove it that at the same time. This is equal to phi inverse of and X is equal to a psi of A plus C the same, and Y is equal to a psi of B, because a psi onto, and this is equal to a psi inverse, and this psi is linear, so if this linear, so this is equal to a psi of A plus C B, and this is here should be phi here. This is AB antemy belongs to V1, should be here phi, and also here phi, which means phi inverse, and this is also phi. Then this is phi inverse, and this is also phi, this is phi, and this is phi. So now this is phi inverse phi will be identity, and this is will be equal to A plus C B. And what about A? A is equal to phi inverse of X. This is equal to phi inverse of X, and C the same, and B is equal to phi inverse of Y. So we satisfy the linearity for phi inverse. This is linearity for phi inverse. This is number 2 without proof. We just prove 1. This is enough. And this is finish our theorem. And this is our proposition. This is page number 1. Now another proposition. Vector spaces with the same dimension are isomorphism. Vector space with the same dimension are isomorphic. Are isomorphic. This is C. So this is without proof. Now we take similar matrices. Take definition. Let AB belongs to Rn times n, the same square matrices. We say A and B are similar matrices if there exists an invertible matrix P. This is invertible matrix such that A is equal to P inverse BP. This is definition of similar matrices. Let AB belongs to Rn times n. We say that A and B are similar matrices. We call it similar matrices if there exists an invertible matrix P such that define this condition: A is equal to P inverse BP. Now we take this as a proposition. Let A, B, C belongs to Rn times n. First, A is similar to A. That means the matrix is similar with itself. A is similar to A. Number 2, if A is similar to B, then B is similar to A. the opposite. If A is similar to B, then B is similar to A. Number 3. If A is similar to B and B is similar to C, then A is similar to C. But this is transitive. If A is similar to B and B is similar to C, then A is similar to C. Number 4. If A and B if A and B are similar, then determinant A is equal to determinant B. That means the two matrices the same determinant. Number 5. If A and B are similar, then TR, this means trace A is equal to trace B, and trace A, this product of main diameter. That means if A is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33, then trace A is equal to this multiply A11, A22, A33. This is trace. If the matrices the same are similar, then trace is equal for both of them. This is page number 2. Now this is definition. Let T from V into W be a linear transformation then number 1, kernel of T is equal to T inverse of 0. Number 2, range of T is equal T of V. This is definition of kernel. This is definition of kernel. What mean kernel of T? That mean kernel of T, the opposite of 0. The opposite of 0. And the range of T is equal T of T. This all image of the elements in V. And here, if we take any example and try to find the image of the kernel, try to find the kernel. Example, let T defined from R3 into R2 by T of X and this is, to be clear, T of X1, X2, X3, because this is in R3, is equal to, this is an R2, X1 plus X2 and X2 plus X3. Question is, find the kernel of T. Solution. How we can find the kernel of T? Kernel of T, make T inverse for 0. Which elements here image of equal to 0? Now we take T of X1, X2, X3 is equal to X1 plus X2, X2 plus X3, and make this is equal to 0, 0. And we get now this is equation X1 plus X2 is equal to 0 and X2 plus X3 is equal to 0. From this, X1 is equal to minus X2 and X2 is equal to minus X3. So if we get this condition for any point belongs to R3, satisfy this condition, the image of this T of this point will be 0. Let that mean point kernel definition kernel of T is equal to point x1, x2, x3 such that x1 is equal to minus x2 and x2 is equal to minus x3. This is definition of kernel. Now we take any point, we can satisfy this kernel, belongs to kernel. Here minus 2, here 2, and here will be x2 will equal to minus x3. So this is minus x2 equal to minus x3. Now we say this is belongs to R3. Is this belongs to kernel? Put it here in T. T of minus 2 to minus 2 is equal to, by defined by this, x1 plus x2, this plus this will be 0, and here x2 plus x3 also will be 0. So this is image of this point 0. This implies that this point minus 2 to minus 2 belongs to kernel of T, and so on. Any point satisfy these two conditions will be belongs to image of T. This not just one point, infinitely many point. Okay, we can take minus 1, 1, minus 1. Can take minus 3, 3, minus 3. Can take 4, minus 4, 4, minus 4, and so on. So this is infinitely many points. Satisfy this belongs to kernel of T. Not just one point, many points. Now if we take example, let T define from R2 into R2 by T of x1, x2 is equal to x1 plus x2, and here 2x1, and find the kernel. Find the kernel of T. The same solution. T of x1, x2 is equal to x1 plus x2 to x1, and make this is 0 because this is always by definition. So this is T inverse of 0. So we have to make equality here for 0 and make get two equation. X1 plus x2 is equal to 0. This get from this x1 is equal to x2 minus x2, and 2x1 is equal to 0. That means x1 is equal to 0. So we get these two conditions. This is page number 3. So now we can define kernel T is equal to x1, x2 and R2 such that satisfy these two conditions. And this if we take node 0 here minus x2 take 3 and here minus 3 and here 3 minus 3 will be, but here not. So this is just if we take x1 equal to 0, should be and also or and x2 equal to 0. Because here if we take point 0 0, this is of course will be belongs to kernel of T. But if we take x1 0 and 3, this just doesn't belong to kernel of T, because this will be here will be 3 and here will be 0, but here not 0. So should be both of argument will be 0. And now can take another example. Let T defined from R3 to R by 2 of x1, x2, x3 is equal to 2x1 plus x2 plus 4x3. Find kernel of T. And this now solution, take T of x1, x2, x3 is equal to 2x1 plus x2 plus x3. And make this equal to 0. And now get 2x1 is equal to minus x2 plus 4x3 we can move this to be easier. This will be difficult, and clear this and also clear this. will be just this. Two x1 is equal to minus x2. And doesn't matter about this. Any point here. Doesn't matter which point here. So now the kernel of T is equal to x1 points x1, x2, x3 such that x1 is equal to minus x2 over 2, because here 2, and here this from the we can get x1 is equal to minus x2 by 2, and doesn't matter about x3. So here if we take a point now, for example, here minus 4 and here 2, so this is minus 2 minus 4 by 2 will be minus here minus will be 2. So and here doesn't matter any point, look like 1. This T of this point 2 minus 4 1 is equal to, by definition, 2x1 2 times 2 plus minus 4. This will be 4 minus 4 will be 0. Doesn't matter about this, we don't need it here. So this is any point will be belongs to kernel. So this is 2 minus 4 1 belongs to kernel of T. I think this is enough for today. Thank you very much, and this is page number 4. Thank you very much. Goodbye.